previous lecture, we looked at function definitions. We looked at function definitions where the definition was just a single line of expression, and we also looked at multiple lines of definition where each line corresponds to some combination of input patterns. Here is another way of defining functions, which is called guarded definitions. Sometimes you might want to define you might want to give some definition in case some condition is fulfilled, and some other definition when some other condition is fulfilled. Like for instance, here is how you might define the absolute value function in mathematics. You might say this is just x if x is greater than or equal to 0 and it's minus x otherwise. Okay. This is an example of a guarded definition. This thing is called a guard. Why are they called guards? Because they guard when this definition will apply. This particular case of the definition will apply if this particular condition is fulfilled, and the next line of definition will apply if that condition is fulfilled. Okay. So this is what you mean by guarded definition. And just like in mathematics, you can write definitions like this. You can directly write such definitions in Haskell, and you can also mix them with pattern matching, right? So for instance, you can say XOR 13, there is an XOR 12 which is missing. So XOR 12 is purely guarded definition. You might say something like XOR 12 B1 B2. In case B1 equals B2, then false. In case B1 is not equal to B2, then it's true. Okay. So that's a guarded definition. But you can also mix pattern matching and guards. Like here, I am saying that if the first argument is false, then whatever is the second argument, you return that. Whereas if the first argument is true, then check if B2 is false. If so, return true. If B2 is true, return false. Okay. So that's another way of writing definitions. Just to tell you that you have lots of flexibility in defining basic functions. So single line expressions, pattern matching, guards. Okay, you can mix and match all these. And remember that you can also express some of these things using a single line expression on the right hand side, which uses if then else. Okay, so there are all these facilities that Haskell provides you. Yeah, so here there are two lines of definitions. The first line caters to the case when the first argument is false. The second line applies when the first argument is true, and in that there are two cases. The first case is when this guard is true, the second case is when this guard is true. And guards also will be processed. So if I provide an argument, let's say XOR 13 B2 true, then it will first check this definition. It will first check that definition. It does not apply because, sorry. It will first check against XOR 13 false B2 equals B2. That won't apply because true is not equal to false. So that definition, this argument does not match that pattern. But the first argument matches this pattern. But then again, it will go into each guard and look at it in order from first to last. It will check whether B2 satisfies this guard. It does not satisfy, so it will go here. B2 satisfies this guard, so it will actually fire this definition. Okay. So okay, so these are guarded definitions. Now some facts about guards. Guards may overlap. So for instance, I might say XOR 14 B1 B2. If B1 is equal to true, then return not B2. If B2 equals false, return B1. And both the guards are true for true false. But only the first one will fire, because the first guard that is made true by the arguments will be the definition that will be taken. So in this case it will be not B2, not false. Okay, if the second guarded definition were to fire, it would say just true, but thankfully in this case there is no difference, because true is the same as not false. But you need to remember when you write guarded definitions that the first guard that is made true will always fire. So this also tells you that you should guard yourself when you write these pattern matching definitions or guarded definitions. You cannot, for instance, write XOR bad. Right? Here is a definition which says the first argument is false, you just return whatever is the value of the second argument. The second argument is false, you just return the value that's provided as the first argument. But if these two cases do not hold, then you should return false. Because if these two cases do not hold, it's the case true, right? But you shouldn't. So normally this XOR, this thing should have been here, should have been the third line, but instead I put it in the first line, and this is bad because every argument will, anytime you provide any argument, XOR bad of false true, what the Haskell engine will do will be to try to match this false true against the B1, B2, and it will match, because B1, B2 are variables and they variable patterns, and they match any value that's provided as the actual argument. So this is a bad definition because it will always return false no matter what. Okay, so you should guard, you should be careful when you do this. Similarly, for guarded definitions, I cannot, for instance, say XOR bad B1, B2 yeah, so it's a little harder to write this here, but we will see examples where you can switch the order of the guards and it will be bad. Okay. Okay. For instance, here I could have a variant of XOR 14 where I say if B1 is equal to true, then return not B2. If this guard does not match, then this is a valid definition. But then if B1 is not equal to true, then it has to be the case that B1 equals false. So I don't even need to provide an actual Boolean expression here. I could just write it as true. Okay, but of course it's clear that you cannot switch up these two values, right? Because if you push this up, then this true will always, true is a condition that is always true, so it will always return the value of B2. So even if I, for instance, invoke this particular function with and this is not what you expect, right? So you should be careful how you order your guards, but mostly you will put very specific cases at the beginning and the more general cases towards the end. Okay, so this is just a something that you need to take care of. Right, so there is another problem with this code, which is that if I invoke it with XOR 14 false true, then neither the first guard nor the second guard is true. So then you will get an exception when you try to run this in Haskell in GHCI, you will get an error saying non-exhaustive patterns in function XOR. So you need to guard against that also. That's a runtime error. A runtime error is something which you will not face when you are compiling the program, but you will face only when you actually invoke the function with some specific arguments. So one way to guard against these non-exhaustive patterns error is to say otherwise at the very end, and otherwise is just an alias for true. Okay, otherwise is just internally defined to be just true. So if you provide true as the last guard, and that will always be satisfied no matter what. So if every other guard fails, you will come to the last guard, and the last guard is just the expression true, which no matter what input you provide, true is always satisfied. So this particular definition will fire. Okay, so we have seen so far single line expressions, if then else expressions, pattern matching, guards. Okay, so various styles are appropriate for various definitions. As you practice Haskell, you will stick to some style, and it is just a matter of idiom which style you choose for which definition. But here is another way of defining functions, which is to use the case expression. Case value of case expression of pattern 1, you do something, expression 1. So the difference between pattern matching and guards is that in pattern matching you can only provide patterns, which are some very specific expressions, whereas in guards you can actually give complicated Boolean expressions. In case, similar to pattern matching, you can only give patterns on the left hand side, you cannot give complicated Boolean expressions. You are just saying if this expression matches this pattern, then the overall value that is the value of this expression is expression 1. If exp matches pattern 2, then exp2 is the value of the overall expression. So that is what you want to say. So here is an example of case illustrated using XOR. XOR 16 B1 B2 is case B1 of false. If B1 is false, then the overall value that you want to return is B2. If B1 is true, then the overall value that you want to return is not B2. Okay, so this is another way of defining expressions. Finally, so this is like switch case in C or Java. So you will say switch B1 case false even though in C you do not return expressions, you have to actually, these are statements, so you cannot just say B2, you have to say something like return B1, return not B2, etc. This is C. Yeah. So the case statement in Haskell is similar to switch case in Java or C. It is an expression, not a statement. This needs to be underlined. Finally, you can next cases. Okay, this is a pathological example, but you might find use when you write complicated programs where you have to nest cases. So case B1 of, if B1 is false, then case B2 of, and this is a pathological example as I said, if B2 is false, then the overall value is false. If B2 is true, then the overall value is true. If B1 itself is true, then the overall value is not B2. Okay, you can mix and match these things. So you have these rich menu of ways in which you can describe functions in Haskell. Okay. So, we will see as we define more and more functions, we will keep using many of these styles, and you will get an exposure to all these styles as the course progresses. Okay. So, now let us resolve one of the issues that we kept as a mystery earlier, which is why is this type written as bool arrow bool arrow bool, whereas normally in mathematics I would have written it as XOR 17 or whatever the number is. It is a function from a pair of bools to a bool, is what I would have written in mathematics or in some other languages. But here I am writing it as bool arrow bool arrow bool. So, let us tackle this issue now. So, recall that we write plus space n space m, not plus applied on n comma m within parenthesis. Normally functions come with an arity. Arity means number of arguments, right. Instead, this is the nice feature of Haskell, it is that it assumes that all functions take only one input. Okay, all functions have arity 1. But how do you handle functions with multiple inputs? Return functions if necessary. Okay, this is very nice. Okay. So, plus applied to n returns a function that adds n to any input. So, this feature is called currying after the logician Haskell Curry. As you may notice, the language Haskell itself is named after Haskell Curry. Okay. So, just to illustrate this, so normally you can think of plus as a function which takes two inputs n here and m here and produces an output n plus m, but in Haskell you would think of plus as a function that takes one input and produces a function plus n. What is plus n? Plus n is something that adds n to every input it receives. So, it receives an input m and it adds n to m. Okay. So, this is the default behavior in Haskell. Every function of multiple arguments is to be thought of as taking the first argument, returning another function, which will take the second argument and return another function, which will take the third argument and return another function, and so on till at the end you will return a function and take you will return a value and take you will take a value as input and return a value as output. Okay. And just to specify this in terms of mathematics, so you can think of multiple, so you can think of plus as one function, right, from n cross n to n, or you can think of multiple functions plus 0, right. What is the plus I function? Plus I function applied on n should give you n plus I, right. So, you can think of one binary function as a collection of all unary functions where the how many functions are there, however many values are there in the first argument. A binary function f from n to n, from n cross n to n, can be thought of as an infinite collection of functions. Of unary functions. This is the important thing. F sub I from n to n for I ranging over all the natural numbers, right. So, this is the point. How do you define the Fi? Fi on n, Fi will send n to f of I comma n, right. So, given a binary function, I can define an infinite family. Instead of saying infinite collection, you typically say infinite family. A binary function, from a binary function you can get a family of unary functions, and if I give you a family of unary functions, one function for every element in the domain of the first argument here, then from that I can get a binary function. So, given, so this is one way. In the other way, given a family right. So, you can always convert between binary and unary functions, you can always convert between binary functions and families of unary functions. But what is a family of unary functions? A family of unary functions is nothing but a function that associates one function to every natural number, or in other words, it is a function from n to n to n. This is precisely the isomorphism, if you will, that Haskell exploits. So, it treats every function as a unary function, right. And this is just a piece of Haskell syntax. Rather than writing f of x, you will write f space x, okay. And this is convenient because if you were to write f within f and the argument within parenthesis, then you would have to write things like this: f applied on x, and then you have to write parenthesis and write y, maybe sometimes put parenthesis here. This becomes unwieldy. So, in Haskell you just write fx y, okay. This is very simple, okay. So, let us return to Haskell. So, this was just to give you a bit of relate this to what you might do in mathematics. Let us return to Haskell. So, plus n maps m to n plus m. So, what is the type of plus n? Plus n is of type int arrow int, because it has an integer as input, it has an integer as output. What is the type of plus? Plus maps n to plus n. Plus n itself has type int arrow int, and the input n has type int. So, it maps int to int arrow int, right. So, this is the type of plus, right, okay. So, suppose I had a plus 3 which added 3 numbers, then plus 3 will take n and return a function plus 3 applied on n, which will take a further input m and return another function which is plus 3 applied on n and m, which will take L and finally give me the value n plus m plus L. Now, if I want to compute the types, plus 3 of nm maps L to n plus m plus L. So, the input is L and the output is n plus m plus L. So, the type is int arrow int, but this is for plus 3 nm. Plus 3 n maps, you see, plus 3 n takes m as input and produces plus 3 nm as output. So, plus 3 nm is of type int arrow int. So, plus 3 itself has type int arrow int. Finally, plus 3 will take n and produce plus 3n. Plus 3n has type int arrow int. So, plus 3 itself has type int arrow int. Okay. So, this is about the types. So, this is why in Haskell you write all the input types like this and put the output type there. But wait, where are the parentheses, right? Because here I had int arrow int. There are these sets of parentheses, whereas here there were no parentheses, right? So, how to explain that? Right, we will explain that in a minute. The point is that Haskell automatically supplies those parentheses, okay. So, consider a function with many arguments. Let us say f x1 x2 dot xn equals e is some expression. Let us say each xi is of type int and E is an expression of type bool. Yeah, then the type of f would be int arrow, you are producing a function, so that will be int arrow, you are producing another function, and so on, till finally you come to this point where you consume an int and produce a bool. Okay, so there are all these nested parentheses. Correspondingly, you cannot write this, you should actually write fx1, because fx1 returns a function, so that can be applied to x2, that returns a function, so that should be applied to x3, and so on and so forth. So you have to put parentheses both when you apply functions to arguments and also when you specify the types, right? But this becomes unwieldy. So Haskell makes life easy for us by supplying the parentheses automatically, right? So int arrow bool without any parentheses will automatically parenthesize the types from the right side, right? So this is what is called right associative. And all you need to remember is that A arrow B arrow C is the same as A arrow B arrow C. Okay, fine. Correspondingly, function application brackets to the left. So all you need to remember is fx1, fxy is just shorthand for f applied to x, which will produce a function, and that function being applied to y. Okay, and instead, and if it were fxyz, then f applied to x, which will produce a function that is being applied to y, which will produce another function, which is applied to z. Okay, so this is what you will have to actually write, but Haskell automatically supplies these parentheses. Okay, so function application is left associative. This is the mathematical term for this behavior, where if I write f x y, then automatically parentheses are supplied like this. Okay, so that is called left associative. Okay, now we will just introduce a few other nice things now that we have seen this currying, etc. So recall that div and mod we introduced earlier, which behaves as follows: div of 29.3 would be 9, mod of 29.3 is 2. We can actually use it as infix operators rather than as functions by providing what are called backticks. You will typically find the backtick below the tilde in on your keyboard, left top, towards the left top. Okay, so instead of writing div 29.3, I can write 29 div 3, and this is a more natural looking way of writing this expression, because div, so this is like saying 29 by 3, okay, except that it is some named function, but you can always turn a named function, a binary function, into an operator by putting these backticks. And this is just like, and this is just the reverse of what you did earlier when we turned an operator into a function by putting plus, star, etc. inside parentheses, right? We specifically we used this not equal to, which is an operator, we used it as a function by putting it inside parentheses. Okay, yeah. So infix operators can be used in prefix form by enclosing in parentheses. So you can say plus applied on 5 and 3, that will give you 8, slash applied on 8 and 3 will give you 2.6665 whatever. And this introduces another new trick, which is just a trick. You don't need to memorize all this, but these are all part of basic Haskell idioms, and as you program more and more, you will get to use these features. Plus is a function that works on two numbers. What is plus applied on n? Like we saw earlier with that PLUS, plus is a function that takes an integer and returns a function that takes int to int, right? So this plus also is a function. So plus applied on n is a function that takes that adds n to any input it receives, right? Plus n is a function that if you apply it on I, will give you n plus I. Now rather than write it as plus n I, you can write this shorthand n plus. Because plus is a binary operator, you can say I want to define a function from a binary operator. I want to define a unary function by fixing the left argument. I can either fix the left argument or the right argument. So I can have n plus, I can have, so for instance 5 plus applied to 3 is 8. Here I am taking the plus operator and fixing the left argument. I can also fix the right argument. Plus 5 applied on 8 is 13, right? So this is fixing the left argument. These things are called sections, right? Plus 5, 3 plus, etc. Recall that I earlier mentioned that you can view each binary function as a family of functions like this. If you think about it, think of it as a table. And in each cell you have a value. Okay, this is the value for 0 0, this is the value for 1 1. Somewhere here would be the value for 4 3 4, etc. Right? Now sectioning, so you can either take each column separately and that's a function, because if you just take this column, that's a function where you fix the second argument and for each value of the first argument it returns a value. So those are, if you take the plane, think of the n cross n plane like this filled with values as a binary function. You can either take these vertical strips or horizontal strips. The vertical strips correspond to sections where you fix the first argument. The horizontal strips correspond to sections where you fix the first argument. The vertical strips correspond to sections where you fix the second argument, and each of those strips are unary functions, and that's exactly what Haskell allows you to use. Okay, plus 5, 3 plus, etc. We will see practical uses for these later. So you can apply this kind of sectioning to other binary operators also, not just plus. Star 8 applied on 3 is 24, 8 slash applied on 3 is 2.6665, slash 8 applied on 3 is 0.375, because this is nothing but 3 divided by 8. This is 8 divided by 3. 8 minus applied on 3 is 8 minus 3, which is 5, but you cannot do minus 8 3 because minus 8 is negative 8. Not the minus function where you fix the second argument. Okay, so you should use subtract instead. Okay, subtract of 8 from 3 is minus 5. Okay, so this is the kind of thing that you can do. Finally, before we end this lecture, we have so far given function definitions where the functions are multi-line definitions, etc. But still, they apply for very limited, for a very limited set of values, a limited set of input combinations. 1, 2, they don't invoke themselves. So recursive definitions forms the bedrock of Haskell. Okay, so we need to understand recursive definitions. We'll just look at we'll quickly look at some recursive definitions for factorial, and we'll refresh this again in the next lecture. In general, you have a base case for the function f of 0 is given. For n greater than 0, f of n is defined in terms of f on smaller values, f of n minus 1, f of n minus 2, all the way up to f of 0. You could use any of these values on smaller arguments, in terms of values of f on smaller arguments. For instance, here is the factorial definition which you would all have seen in school and in other programming languages too. 0 factorial is 1. For n greater than 0, n factorial is n times n minus 1 factorial, and you can just transcribe it as a definition in Haskell. Factorial of 0 is 1. Factorial of n is n times factorial of n minus 1. Okay, so that's a definition. Remember that I said that integer represents integers of arbitrarily large magnitude, and you can actually in Haskell, I'll show you this GHCI session later, you can invoke the function factorial on 40 and you will get actually the actual value, which is a large number which cannot fit inside 64 bits. Okay. Int has lower and upper bounds. Okay, sorry, much larger than 63 minus 1, I must say. Int has lower and upper bounds, minus 2 power 63 and 2 power 63 minus 1 on most 64-bit machines, but integer doesn't have. Okay, fine. So notice that you write factorial, recall that I said that you will write f of x in Haskell rather than f with parenthesis x. Okay. But here you will notice that, so in math you would say f of n minus 1, but in Haskell you would say f space. You cannot say n minus 1 because you are applying f on an expression as a whole, and that expression has to be inside parentheses. Okay. So in math you would write f and n minus 1 without the space, there is a space here. And this n minus 1 is put inside parenthesis not because it is an argument, but because this parenthesis is to whereas these parentheses are to indicates right. So it's a complex expression. So yeah, it has to be, whenever you want a complex expression to be treated as one unit, then you will put parentheses around it. If instead I had written factorial n minus 1, that would be interpreted as factorial n minus 1. That would be a wrong definition because I mean Haskell will compile, but factorial n makes factorial n as a recursive call, so it will never end. Now even in this definition there is no guarantee of termination, because what if I invoke this factorial function with minus 1 as the argument? Yeah, factorial, and the minus 1 should be enclosed within parenthesis because I want to treat it as one value. Okay, if I just write factorial minus 1, that will be treated as 1 subtracted from the factorial function, which doesn't make sense. It won't even type check. But anyway, if I do factorial minus 1, it will never terminate. So if I want to force it to terminate, I can do something silly like this. Factorial 0 is 1, factorial n, if n is greater than or equal to 0, I will do n times factorial n minus 1. Otherwise, this means that n is less than 0, I will do n times factorial n plus 1. I will count from below towards 0. I could do that. Or this is something that we will see more of later. Whenever you have a situation where there is a possible error, then you can actually write error. Error is a function that you can place in any function definition and you give an error message as argument, okay. So you can apply the error function on any error message and place it as part of any expression. Of course, it should type check, etc. If it does, then yeah, so then this is a much better way of writing the factorial function, because it tells the user that you are not expecting negative inputs at all. Okay. So to recap, we have seen further ways of defining functions, mainly using guards, and then we looked at why in Haskell you write the types of functions as int arrow, bool, etc. because in Haskell every function has only a single argument. And we looked at sectioning, which is a useful trick which you can use sometimes in as part of more complex expressions. And finally, we have started looking at recursive definitions. We will continue with this in the next week. Thank you very much.